In engineering, when an object is designed, a technical drawing is used to represent it graphically on a screen or sheet, so that engineers, workers, and users can communicate with each other and understand what it looks like. In this video, we will look at the basics of learning how to read a technical drawing, so that in just a few minutes, you can correctly interpret the various elements of it. There are various regulations that define guidelines for producing technical drawings, such as the International ISO system. But in this video, we will only look at the basic principles that are generally common to each standard. Let's take a very simple object. This shaft has many features. Let's look at its engineering drawing. In order to represent the object on a sheet of paper, some of its projections are required. In other words, graphic representations that describe the object. As it can be seen, there is its three-dimensional representation, an aid, not always present, for immediately understanding the shape of the object. The projection is in isometric axonometry, meaning that the XYZ axes form three equal angles of 120 degrees. Then we have the multi-view orthographic projections. To understand the shape of this object, we need three of them. In essence, there are up to 6 two-dimensional images representing perpendicular views of the object. But the first thing to do to understand orthogonal projections is to read the title block, a table, usually in the lower right corner, in which all the primary information is enclosed. It usually includes the company logo and the designer's name to know who to contact, a title, code, or drawing number, and anything else needed to identify the object and track it down, usually in a separate cartouche, the revision number and date to tell if it is the latest version of the drawing and when it was made. Then there are the scale of the drawing and the paper size it needs to be printed on to get the correct scale. These two pieces of information are related. The drawing of an object most times doesn't have actual dimensions, but they are scaled to fit into the dimensions of a sheet. If the sheet is printed in the indicated format, then the scale will be correct. In this case, the scale is 1:1. It means that actually the drawing is in full scale and has the same dimensions as the real object. So if we take measurements directly from the sheet by means of a ruler, these will be effective. While if it is written, for example, scale 1:2, it means that the object is drawn reduced by half of the real size. In practice, the dimensions we measure will have to be multiplied by 2 to understand how big it really is. On the other hand, if it is written 2:1, we are dealing with an enlargement. The object would be drawn twice as large as it really is, so we have to divide the measured measurements by 2. Another fundamental thing is the symbol to define whether the orthogonal projection used is of the first angle projection, the European projection, or the third angle projection, the American projection. The orthogonal projections are not randomly arranged. They are aligned with each other by one of these two standards. With the first angle projection, the object lies between the observer and the projection planes. By imagining a cube surrounding the object, each view is projected onto the inner walls of the cube, which is then unfolded in order to create all views. For simplicity, it is like laying the object on the paper and rolling it to arrange the various views. In contrast with the third angle projection, it is the projection planes that are between the observer and the object. Imagining the cube surrounding the object, each view is projected onto the outer walls of the cube to then be unfolded. For simplicity, starting from the front view, we have its right view, top view above, bottom view below, etc. The exact opposite of the first angle projection. General tolerance is also present. In orthogonal projections, there are dimensions, numerical values that are the actual dimensions of the object and which are expressed in millimeters in mechanical drawings. At the time of production, where one cannot expect absolute perfection, this data allows one to understand how precise the manufacturing must be. In this case, where it says plus minus 0.10, it means that the tolerance is 0.2 of a millimeter, So in this 41 millimeter dimension, it's accepted a manufacturing error that can be plus 1/10, that is 41.1, or minus 1/10, that is 40.9. A tolerance can also be specific to a given dimension. Similar to the above, there are undimensioned fillets and chamfers. These general figures must be taken into account unless a fillet or chamfered edge is specified in the dimension. Lastly, there may be additional lines which specify finish, surface roughness, or other features of the part that cannot be drawn, such as the material, which in this case, as the acronyms of the AIC and SAE designation systems say, is common 304 stainless steel. Now let's move on to the actual drawing. As we can see, it is made up of different lines, of different thickness, continuous or dashed. Each one has a meaning. The thick line defines all the contours and edges that can be seen in that view, while the dashed line shows those that cannot be seen in that particular view. A dashed dot line, on the other hand, indicates symmetry if the object on either side of the line is substantially mirrored. They are also used for holes. A dashed dot line may also indicate a section if there are arrows indicating the direction of the view and letters that are shown in the actual section drawing. A section is an internal view of the object. If we're looking at it, there are crossed-out fields with 45-degree lines representing the internal surface of the object, as if they were the cut surface of the solid. While a detail is an enlargement of a certain area, always named by letters, where usually irregular lines interrupt the drawing, leaving only the necessary parts. Dimensionings, on the other hand, are represented through thin, continuous lines, which placed side by side with numerical values, can indicate lengths of the various parts of the object, fillets if the letter R is present, diameters if the symbol phi is present, chamfers by specifying the height and degree of inclination. They should always be arranged externally in relation to the projection and can be attached to visible lines and axes of symmetry. Therefore, they are placed internally only if necessary, and hidden lines are not dimensioned. For these reasons, there exist other views and sections. Threaded holes, on the other hand, are represented as two concentric circles representing the root and crest of the thread. Usually, threaded holes are defined according to the ISO standard, which consists of an abbreviation, in this case M6, which specifies the diameter of the hole to be made, and the diameter of the thread to be made inside it. After an X, the fine thread may be reported. If it is not present, it is implied that you are using the coarse thread. And after another X, the length of the threaded hole is reported. Often, the hole has a countersink or a counterbore that serves to accommodate the head of the screw, which is specified with dimensionings and is standard according to the type of screw. Along with the dimensions, one can also indicate the surface roughness index of that particular face, which may deviate from the general roughness index. Finally, there may be notes for machining processes or warnings. Now that you have understood the basic principles of technical drawing, you can use it to create an object or design a project yourself.